Welcome to EDU World Space.
So we're going to solve a problem where we have a uniform wire of mass big M. Uniform mass is uniformly distributed over the wire, and the wire is curled into a half circle or semicircle. And we have Y here and X here. So we have this mass distribution, and then we're just going to put a point mass at the center of the half circle. And so we want to sum up all the gravitational forces to each differential piece of mass on the half circle. And we'll call this d phi, and d phi is the phi is the angle between a positive x-axis and the point where this differential mass is. Now, we are looking at an attractive force. When we're looking at gravitational forces, we were looking at an attractive force between two masses. You can think of them as 2-point masses for now. And we know by Newton's universal law of gravity that the force due to this little differential piece of mass on this point mass is going to be, I'm going to draw it as dF equals the universal gravitational constant times the point mass times the differential mass over the distance between the two masses squared. I'll put R here. That's R. Okay? All right, and it's going to be an attractive force, so it's going to be directed radially from the force on this point mass to the differential mass is directed radially outward. Okay? Now, this is a vector quantity, so we have to be careful to take that into account. And we can break this up into two forces. Call this dFx and dFy. Okay? And really this should be dF. Okay? So we can write, and we'll work this, let's get that y in there a little bit better. So we'll write dF equals dFxi plus dFy j. And the total force due to all of these little differential elements will be given by the integral of these guys. So you just integrate. The total force of the net force acting on this body is equal to the sum of the forces that are acting on it. Now, the x component, if you were to look at a piece over here, the x component here, dfx, is seen to cancel that one out exactly. So we know that there will be no component of the force in the x direction. Symmetry implies that the sum of the forces in x direction equals 0. So we'll just put that as 0. Now dFy is equal to, it's just the the right triangle here, so it's equal to the hypotenuse dF times sine of phi. Here's dFy equals dF sine of phi. So we can plug that into our integration, and I'm just going to write this as F net equals that. So F net equals the integral of df sine of phi times j. Well, df, the magnitude at least, is given by this guy right here. So I can rewrite this as the integral of r's constant. I can take that out. The little lowercase m is constant. And then we have dm, and then big M, sine of phi. Okay, so what is dm? Well, dm is the arc length of a circle. And the arc length is just equal to r times d phi, but it also has mass, so it has units. So if we let mu equal the mass over length, we can write d big M as mu r d phi. That's just a differential piece of mass. And we can plug that in there now. And we get g little m over r squared times mu sub r times d phi sine of phi 0 to pi j direction. Okay, and we do this integration. Fn equals g lowercase m times mu over r times minus cosine of phi integrated from 0 to pi. If you work that out, you'll see that the answer is 2, and then we can write Fn equals g lowercase m times mu over r squared times 2. And that's just the magnitude of it. Let's take this guy and plug it in here, and we get Fn is equal to 2g little m big M over L r squared. But L, if we look at a half a circle, the length of this thing is just equal to pi times r. So if I want to get rid of r in terms of L, I can write r equals L over pi. And I did something wrong here. Oh. A little mistake here. That's just one r. Oops, made a mistake. Everybody does. It's okay. So let's put r equals L over pi in now, and we'll get 2g little m big M over L squared times pi. And that's how you work out this question.